What I'd like to do in this video is go over energy and how it relates to thermodynamic systems. So if I asked you, what are some forms of energy, and you've taken some high school physics classes or you've taken college physics classes, you might tell me that I think there was a form called potential energy, and I think there was a form called kinetic energy. And you'd be right. But additionally, there are other forms of energy that a system has. A system might have thermal energy, might have nuclear energy, might have chemical energy, and it might have other forms of energy. Now, if we add up all these different forms of energy that a system has, we're going to get the total system energy. Now, in thermodynamics, we're concerned about macroscopic systems, or macroscopic energy, and microscopic energy. Now, macroscopic energy is what you're going to be what you were most familiar with, and it's going to be your potential energy and your kinetic energy. And the macroscopic systems are going to be concerned with the motion and position of the system as a whole. And that makes sense if we look at the equation for potential energy, mgh, where h is the change in height of the system, and kinetic energy, which is 1/2 mv squared, and the kinetic energy depends on the velocity of the system. Now, your microscopic energy is going to be all of these other energies combined. And we're going to give this a name. We're going to give it a name of internal energy. And we're going to give it a symbol of a U. And this microscopic energy is going to be related to molecular structure and molecular activity of the system. So with this, we can write an equation for the total system energy. So we can write it for the change in the system energy. So our change in the system energy, so our change in the energy is equal to the change in potential energy plus the change in kinetic energy plus our change in internal energy. And if we expand this out another step, we're going to have energy at some state 2 minus energy at state 1, so that's just a change in energy, is equal to potential energy at state 2 minus potential energy at state 1 plus the kinetic energy at state 2 minus kinetic energy at state 1 plus internal energy at state 2 minus internal energy at state 1. And this right here, or both of these equations, are equations for the total system energy and are very useful. So now, in my last video I did a very long time ago, I had talked about work, and besides work, closed systems are able to interact with the environment by energy transfer of heat. So if we have energy transfer of heat, we're going to give it a symbol of Q. And just like work, Q can be positive or Q can be negative, and they mean different things. So if our Q is positive, that means the heat transfer is, I don't like that color, I think it's too hard to read, is 2 the system. So it's into the system. If our Q is negative, then our heat transfer is from the system. And this is opposite of the sign convention we had for work. So for work, our work could be positive, our work could be negative. And if our work was positive, then it was work that was done by the system. And if our work was negative, that means it was work that was done on the system. Now, if you learn this better visualizing it, if we draw a system and we have heat going in and we have work going in, if our heat's going in, then our heat is going to be positive, and if our work's going in, then our work is going to be negative. If we have heat coming out and we have work coming out, if work's coming out, work is going to be positive, and if heat's coming out, heat's going to be negative. So they're opposite of each other. The sign convention is opposite. So just take a moment, make sure you understand, make sure this makes sense in your mind, and just take a moment. It's pretty important. Now, the other thing with heat is, just like work, if we're going from a state 2 or state 1 to a state 2, this energy transfer of heat is not a property, because the area under the curve is going to depend on the details of the process. It's going to depend on how it goes from state 1 to state 2. And the area of the curve under the curve is going to be different depending on the process. So this heat transfer, energy transfer of heat, is not a property of the system. Now, I would just really like to briefly mention the 3 modes of heat transfer. So the 3 modes are going to be conduction, convection, and radiation. And that's pretty much all I'm going to say about them. Besides, if you're a mechanical engineer, you're going to take a class called heat transfer, and you're going to go into depth on all of these processes, all of these modes of heat transfer. And they can get pretty complicated. So you can even take a graduate course on each of the different modes of heat transfer that lasts a semester each. But in thermo, when I taught thermo, we weren't really concerned with the intricacies of what's going on in each of these modes. We just wanted to know that they're there, and this is how energy is transferred. So that's really all I'm going to say about these modes of heat transfer for right now. But I think we do have enough to go over what the first law of thermodynamics is. And it's not too bad. It's essentially that energy is conserved. So if we want to write the equation for the first law, if we want to write the energy balance for the closed system, we're going to have a change in the amount of energy within the system over a time period. So that's just going to be some change in E, delta E. And this is going to be equal to the net amount of energy transferred in across the system boundary by heat transfer during the time interval. So that's going to be Q. And it's going to subtract the net amount of energy transferred out across the system boundary by work during that time interval. So minus W. Now, we can sort of write this in an alternate form. If we use this equation for energy right here, we're going to have our change in potential energy plus our change in kinetic energy plus our change in internal energy is equal to our heat transfer minus our work. Energy transfer of heat minus energy transfer of work. And right here we have our energy balance equation. Now there are some alternate forms of this energy balance equation. If I ever do an example that needs them, I'll introduce them there. I think they'll make this a little bit harder to follow. And I think I put everything on one layer because I didn't think ahead. So when I do this example, we're just going to have to try to make room somewhere. Or I guess I can try to erase this. Get a little box. Okay. So with my example, what I want to do is I want to have a system. So I'm going to have a closed system. I'm going to have hot water that's in this system, or a hot liquid. And it's going to be inside this rigid tank. So I'm going to define my system like this. It's going to be hot water inside a rigid tank. And we're going to have this paddle in here. This paddle is going to be connected to some type of shaft that's rotating and is going to be performing work on the system. It's going to be doing 100 kilojoules of work on the system. The system is going to be losing 500 kilojoules of heat. And we're going to be given that our starting internal energy is equal to 800 kilojoules. And we want to know what our ending internal energy is. So to find this, we're going to use the first law, our energy balance equation. So if we write our energy balance equation, we have our change in potential energy plus our change in kinetic energy plus our change in internal energy is equal to our heat minus our work. And our potential energy and kinetic energy are going to be 0 because our system's not moving, our system is stationary. This entire green box that I've drawn, it's not moving, even though the water inside could be. Now, we can write this slightly different. We can say this is going to be U2 minus U1 is equal to Q minus W. And this is where we have to be careful about our sign convention. So right here, we lose 500 kilojoules of heat. What does that mean? That means heat's going this way. Q is leaving. If Q is leaving, it's going to be minus 500. So Q is going to be minus 500 kilojoules. Then we're going to have a minus. This minus sign is not just with this work, it's Q minus W. So our work, what is happening? 100 kilojoules of work on the system. Work is going to be less, if work is done on the system, it's going to be less than 0. So right here, it's going to be minus 100 kilojoules. And here we're going to still have U2 minus 800 kilojoules is equal. So U2 minus 800 kilojoules is equal. If we solve for U2, we're going to get U2 is equal to 800 minus 500 plus 100. And this is going to be equal to U2 is equal to 400 kilojoules. So 400 kilojoules is the final amount of internal energy.